but not tell. And our next speaker will be Ricardo Silva, who is currently doing a postdoc in the lab, and his title is up there. Just gone. Factorial mixture of Gaussians and the marginal independence model. Thank you, Ricardo.
Okay, thank you for coming. This is joint work with Zubin Garamani, but I should actually call this work in progress. They're trying to finish that by next week. So hopefully maybe you can come up with some suggestions for that. The goal, quite simply, is just to estimate a distribution under some marginal independence constraints. There are several reasons why you're interested in a distribution like that. If you look back at some of the talks you had during this year, for example, Mike West's talks on sparse factor analysis, you can imagine some problems where the observations, what I'm calling Y here, are generated by some mixture of latent variables. And you have a sparse model where only a few of the latent variables are used to generate a particular observation, a particular variable. And if you look, in this case, for variables that don't have a common latent parent in this graphical representation, these variables are going to be marginally independent. So he gave some examples on sparse models using gene expression analysis, for instance, where many of these observations don't share common parents, so they are marginally independent. There are other situations where these marginal dependencies are useful. You have a model here for multivariate regression, where I try to predict a vector y given a vector x. So here you're not predicting a scalar, but a vector y. And the joint distribution of this y given x is not factorized. They have some dependencies between these variables, but only between a few of these pairs. So here I'm representing the possibility of a hidden variable causing association between these two output variables, even after condition on x. And this distribution here is generated by variables after conditioning x has marginal independence between variables that don't share a common latent parent. And there are all sorts of situations where this arises. You have here a dynamic model where observations are generated by a layer of hidden states. The hidden states themselves are generated by a window of independent common causes that are going to create associations over a few blocks, but are going to still still going to generate a few independencies over distant points in this chain. And in order to model these problems, I want to take the most general approach. I want to take models where I don't want to make assumptions about which type of latents are there. How many latents, for example, are connecting these two variables in the original model with hidden variables, nor how these variables are connected among themselves. And to make things simpler, I'm going to use this notation where this graph here represents, through bidirected edges, the existence of some hidden variable connecting these two observed variables. So for instance, that model that I showed, the dynamic model that I showed before, has this moving window of bidirected edges representing some common factors that connect these variables. Okay? So to put that in a broader context, this is particularly interesting on models that have series of regressions such as this, where I have several variables y that is generated by a function of other variables plus some additive error, where this error over all these variables y's are not independent. They have some dependency structure connecting them. But this dependency is still sparse. It means that a few of these e variables here, these error terms, are marginally dependent, but many of them are marginally independent. This is a sort of abstraction of the problems that I showed you in the previous slides. So the goal here, in general, in motivation, in practice, in many senses, is going to model error distribution. Although in the next slides, I'm just going to ignore this context, just show in general a distribution of marginal independencies. So why not use latent variable models? As I said, I want to be as generic as possible without using particular assumptions about the latent variables. If you have a sparse model, many of these variables are going to, many of these latent variables models are going to have redundant parameters to begin with, and you have to worry about which constraints are going to impose these parameters to get some identifiability, or just to get a simpler model to compute. It's also interesting to see what would happen in the Bayesian case when you put priors over these parameters. If you have many latent variables there, these extra latent variables are going to, in general, cause an extra autocorrelation in your Markov chain. If you could just integrate them out of your model to begin with, and you just put a prior directly in your parameters of the marginal distribution, then in general, that will reduce the autocorrelation of that chain. Also, if you just exclude these latent variables, you're not introducing a model, there is less difficulty in putting priors over these joint distributions. But this talk, I'm not going to talk about Bayesian methods for learning distributions with marginal independence, but instead, I'm going to focus the maximum likelihood case. So to give an example to motivate a parameterization of a model of marginal independence, let's start with the latent variable case. Suppose I have these 6 observed variables, y1 to 6, and I have some hidden variable z. Here, after integrate out the hidden variables, I may have this bidirected graph structure indicating which pairs are not marginally independent. So given these bidirected models, some people have been trying to create models and algorithms based on these marginal independence constraints. But so far, the case has been applied to Gaussian models, to multivariate Gaussian models, and to binary models. This is a recent paper in the Journal of the Royal Statistical Society about how to fit binary models of marginal independence. And I've done some work with Zubin on Bayesian inference in Gaussian models, but nothing besides that, these 2 families of models. Here I'm going to this talk is concerned about the mixture of Gaussian models. And the mixture of Gaussians usually is described as a model that has indicators telling you which mixture component the data point is generated from. So since this is a latent variable 2, which will be part of my model. What the latent variables I'm not considering explicitly in a model are just the latent variables that are going to create this marginal dependence among the observations. So also, this is not a type of approach that you are going to use in a large P, small n kind of problem. I'm going to focus here on small problems that I try to solve with a particular algorithm that doesn't scale too well, but scalability is something that I'm not concerned right now. It's something more for the future. So you might think that a mixture of Gaussian models of independence might be easy to solve. Just start with your traditional Gaussian model with some marginal dependence constraints and mix them with a latent variable indicating the mixture component. So here, given C, the covariance matrix of y1, 2, 3 has a structure that tells y1 and 3 are marginally independent. But of course, when you marginalize out this latent indicator of the component, these independence disappear. You can just use an approach like that. In order to introduce these marginal independence constraints, you need some type of vector representation of the mixture component, where you associate different mixture component indicators to different sets of variables. There is more than one way of doing that. I'm describing one particular way where if you look at the bidirected graph that is generated from some hypothetical latent variable model, you associate a mixture indicator with each click in this graph. So in this particular case, you have 3 clicks. You're going to have 3 mixture component indicators in a mixture model. And how is this model parameterized? Again, let's start from the latent variable model, which is somewhat simpler to understand. In this model, I'm choosing to generate y1 from its latent variant z1 by a linear combination of an intercept term and a rescaling of z1 and an error term. But these coefficients are picked from a pool of coefficients that is indexed by a subset of the mixture component indicators. So here I'm indicating that I have y1 belonging just to one click, so it's associated just with the mixture component C1. And when I generate y1, I pick mixture components that are indexed just by the first, I pick coefficients that are indexed just by the first mixture component. here I'm assuming all variables are binary, or mixture components are binary, so I have two choices of each coefficient here. And the same thing for the variance of this error term. So if I look at y2, y2 is generated by these latent variables that comes from these two different clicks, that might come from these two different clicks. And therefore, these coefficients that I'm choosing here in this linear combination are indexed by a different subset of mixture indicators. So since this variable is associated with this first click, this coefficient is indexed just by the first mixture component. And this variable is associated with the second click, so these coefficients are indexed by the second mixture component. So if you just imagine what would be the covariance matrix generated by this mixture model. When you marginalize out the latents, the respective covariances is taken by multiplying summing over coefficients associated only with the clicks of yj that are common to yi and yj in this case. Which means in general, and the same thing for the means. If you look at the means that are generated by this model, they are indexed just by the clicks that contain yi. So this means in general, this conditional model of y given these mixture components has a set of identity constraints. If I look at the covariance of yi and j for a particular choice of components, these two parameters have to agree whenever these two vectors of mixture components assume the same values on the intersection of the clicks of yi and yj. So I have all these sets of equality constraints in this case, and then I can just consider that my pool of parameters is indexed only by subsets of these indicators. So for instance, my variances are not indexed by the whole vector, but just by the clicks that contain yi. My covariance yi and j is indexed only by that intersection. The means also indexed just by a particular set of clicks. So whenever you observe the indicator, it's just going to assemble a mean and a covariance by going to this pool of different parameters and generating this matrix and vector. Okay, so what's the size of the parameter space? If you consider the size of the larger intersection, if you look at that any two pairs looks at what clicks they belong in common, see which one is the largest set of in common clicks, and you bound the number of values in the mixture indicator by a constant k, you're going to have this expression to indicating the size of the number of parameters, where this is just the number of edges in the bidirected graph, and this is the number of variables in your domain. So notice this is not quite a simple function of sparseness, because if you had a fully connected graph, would have only one click there, and presumably your number of parameters would be smaller for a constant k. But you can have some notion about the number of parameters from some graphical criteria, such, for example, in decomposable models, the number of click intersections that you have is just the branch factor of the junction tree that you build out of this decomposable model. So how do we estimate parameters of these models from data? You can take a EM approach for that. You write the expected log likelihood of the data, condition on some distribution of the mixture components given the previous parameter values. It already seems like a very costly function to maximize, because here I'm summing over all combinations of mixture indicators, which can be quite large. But on top of that, I have another difficulty, is that for any combination of C values, the resulting matrix has to be positive definite. And when I do my maximization, I have to respect these constraints too. So I'm going to first, most of the rest of the talk, I'm going to concentrate on how to solve that exactly, which is a very costly operation, but still doable for some reasonable problems. And if I have time, I'm going to just brush over very quickly in the end, showing some type of approximations you can come up with. So one particular way of doing this maximization is just doing a simple gradient descent over that, respecting these constraints. But this is a particularly complicated way because it's very easy to jump out of your valid set of parameters. So I'm going to do a maximization where I'm updating just a subset of the parameters while keeping everything else fixed. And to do that, I'm going to borrow an idea from the Gaussian case, where you are going to fix the parameters for the covariance matrix, excluding one row and one column. So, doesn't work anymore. We are going to try to fit one row and one column of the matrix at a time, keeping everything else fixed. In the Gaussian case, there is one standard way already of doing that. There's no iterative conditional fitting algorithm. That if you have a marginal independence constraint, you reparameterize this covariance matrix by using a series of regressions of each variable given everybody else anteceding it in a particular order. So when you want to fit the covariance of Y3 with the other two random variables here, you're going to build a regression model of Y3 given the other two variables. But in this regression model, the coefficients are not independent. This coefficient corresponding to the pair that is marginally independent turns out to be a deterministic function of this other coefficient in the covariance matrix of Y1 and Y2. So it can actually be shown that this is equivalent of getting the residual of Y2 after regression of Y1. And after doing that, you regress Y3 on this residual. And you get an estimate of this parameter, which you can then go back to find this other parameter and rebuild the covariance matrix. What will happen in the mixture of Gaussian cases is a much more complicated problem. If you start again from this idea that are going to transform this parameterization in a series of regressions, but on top of that, you have some mixture component indicators. When you do this parameterization, you're going to make your variable depend on all mixture indicators that you have in your model. All right, so in this case, what happens is you're going to regress yi on those residuals that I mentioned, but the number, but these coefficients that I have here are now indexed by all components. So you have here what seems to be an exponential number of parameters, even though in the original situation you had a tractable number of parameters in a sparse model. So what happened in this case is that you still have those equality constraints among the entries in the covariance matrix. So when you re-express these covariances with this parameterization mentioned to you, these equality constraints are still going to exist. And you have to optimize them taking account this information. So it's a constraint optimization problem that you have when you're doing this parameterization. So it turns out at least you don't have the positive definite constraints anymore if you treat the variance of the, if you just assume this variance, the variance of this term to be positive. This is equivalent of having a guarantee that these matrices are going to be positive definite. It's just equivalent to something called Schul's complement. So in this constraint problem, it seems that we're not really doing anything particularly useful to us if you're going to create an exponential number of parameters on top of the exponential number of constraints. What is going to happen here is one way of solving that is just use these equality constraints to define a small basis for your parameters, which is going to be of the same number as your original parameter space. And just rewrite your conditional log likelihood function as a function of this basis. And once you do that, you have an optimization problem with some quadratic constraints. I'm not going to explain exactly where these quadratic constraints emerge from, but they come from the fact that you also have variances equal to each other across some combinations of mixture components. Because you have these variance equalities, you're going to have some quadratic constraints tying your parameters. So you have this optimization without equality constraints because it transformed everything to a particular basis, but we have these quadratic constraints on my model. As it turns out that you also first fix the variances and try to fit the covariances. We, instead of equality constraints, are going to have some inequality constraints in this case with some nonlinear function p's. You can fit p's in this particular case with these inequality constraints, then fit the respective variances of the error terms that you have in this reparametrization. Again, the number of parameters is acceptable for sparse models, but you can never get rid of this number of exponential constraints. You can have some relaxed variation of this problem where you are going to optimize these coefficients b's, but they're going to throw away the variance equality constraints. And once you throw away these variance equality constraints, what you have in your conditional maximum likelihood estimator is a function that is quadratic in your parameters with some linear equality constraints, just like you had at the beginning before, just after doing the transformation. So in this relaxed problem, I can actually find efficiently the maximum likelihood estimator for B for that while condition on all other variances. But because I'm throwing away some of the constraints, the result is the solution might be invalid. But I can start from this point and project back to a valid set of parameters. And in practice, this seems to do something quite reasonable. In many cases, when you do this projection, you don't actually going to increase back your log likelihood. But it might be the case that this relaxed approach that optimizes without some of the constraints and then projects it back might increase the log likelihood. Oh, sorry, decrease the log likelihood. So you might want to reject this particular update and just use the exact algorithm. But the advantage here is once you fit P for this, you can fix gamma in this particular case when you drop the equality constraints, make things solvable in one step, and after doing that, optimizing those parameters gamma becomes relatively easy. It's simple. It's a much simpler optimization problem than the original space. So just summarize what I did here. I'm taking this idea again of iterative conditional fitting of condition in most of the covariance matrices except for a row and a column. I'm transforming to other parameter space where my positive semi-definite constraints become some sort of quadratic inequality constraints, which in a different space. But it allows me to create some type of relaxed algorithm that is relatively efficient, where I can solve most of my optimization, or I can find most of the parameters in just one pass without an iterative scheme. So it doesn't have, this relaxed algorithm doesn't have any constraints anymore, but you still have to pay a price of converting from the original parameterization for this other parameterization. So you're not getting rid of the intractability there. Even though at this stage you have no constraints, we have to do this transformation, which is also expensive. But you only do this once. So you don't do that at every iteration of maximization procedure. In this case, the constraints, as I said, are just one side of one type of problems I have. The other problem is summing over all configurations of the mixture components, which is exponentially the number of clicks in the graph. And ideally, we would like to use some approximation for this distribution. One standard way of that is doing some variation approximation where you decouple all the mixture component indicators. They become marginally independent in this approximation. But you can't use, there is still not enough for this type of problem. Even if these mixture components are independent in approximation, you still have those positive definite constraints that are going to tie together all parameters that you want to optimize. So this is not enough in order to try to optimize this problem in larger sets. There are alternatives you can think of. Right now, we're exploring the simplest one you can imagine. It's something I call in budget variation approximation, where we approximate this distribution of the mixture component indicators by a distribution that has 0 in most of its configurations, has probability 0 in most of its configurations. So in the approximation, you allow only a few of the combinations to be known, to have a probability non-zero of happening. So when you do the summation becomes tractable. But there is still some work that you have to do on what is the best way of allowing which configurations to have a non-zero probability. So there's still some work in progress. And you have to pay attention that this doesn't guarantee any positive definiteness of those matrices whose combination of C's has probability 0 in this approximation. So if you can estimate all parameters if you choose your set of C's wisely. But when you do a prediction and you generate that covariance matrix given a choice of components, this covariance might not be positive definite. So you have to, for example, project it back into this cone of positive semi-definite matrices before doing the prediction. So the model itself would include a projection every time this matrix is generated. So you're still implementing that. It's not a particularly easy method to implement. Believe me, I tried to use some pre-existing libraries. It's not that easy to make it work. You might think on some extensions on how to control for overfitting. If there are too many parameters, you might want to tie them together by some shrinkage, some regularization term. And try to move it towards to defining models that are close under marginalization in general, not only marginal independence models, but some models of conditional and marginal independence constraints that are close under marginalization. So also you can think of the Bayesian version of that. Can start from one of the simplest priors you can imagine, put Gaussian priors over the covariances and gamma priors over the variances, multiply them together, renormalize with some gigantic indicator function saying it's only the combinations that generate a positive definite matrices are allowed in the prior probability. And you might even use that relaxed fitting algorithm that I mentioned before as a way of generating parameters from the posterior in a Metropolis Hastings scheme. So you can do Gibbs sampling there. The condition probabilities will just be of no canonical formula. But you can try to use those procedures to adapt as proposed in a Metropolis Hastings scheme. In one sense, this problem is doubly intractable, which is just a way, in my case, of saying that each step in the Metropolis Hastings algorithm might be intractable by itself. Because when you generate, you have a intractable number of constraints. The question is there a way of scaling up this algorithm for large problems, even though each step might be intractable? You saw Ian Murray here presenting last week some approach for undirected models where you have a large normalizing constant that don't know how to compute. But there are still approaches that where you can do exact sample from these models. But instead of a normalizing constant that I can compute, I have this big indicator function that I have to respect. And the question is, can I do that? Can I do a sensible Monte Carlo method under this condition? Okay.
Thank you very much. Maybe one quick question before we move on.
Yeah.
What sort of signs of covariance matrix are you thinking about, and how many constraints does that mean you have?
Well, it depends on what, it's going to depend on that shape overall.
But what sort of problem are you trying to do at the moment, which is proving difficult?
Well,
is it hundreds or thousands or tens of thousands?
Again, it depends on the number of clicks in your problem. It's not only a matter of the number of vertices you have, the number of random variables, the number of clicks. And so far, the problems I've been trying now are too small. But if you have a problem with, say, even something like 15 clicks, each step is going to be really expensive. Even that you might, in principle, be able to do that approximately or exactly. Might still want some approximation, but it's going to be really slow.
And how big of a thing?
So the problems I'm using now is still very small. I mean, I'm doing something like with 6 variables per click. There is one particular step here that requires inverting matrices. Inverting matrices of n by n, where n is a number of variables. This might be expensive too, but in general, you're expecting to have sparse models. So even if you have many variables, inverting these matrices might still be not too difficult if your matrix is sparse. Okay. Yeah.
So MATLAB's no good. What are you going to try next, or what have you tried after that?
Now, what I'm doing right now is the simplest thing possible. I get rid of my quality constraints by just directly re-expressing my set of parameters. I express a set of parameters as a linear combination of others, just plug them together, and then I get rid of the quality constraints. And I'm doing something really, really simple, a gradient descent method that just rejects when it goes out, when it violates a constraint, and goes back to the original space if some constraint is violated. Just because I have to do that by next Friday. This is something I'm trying to submit to a conference, but I'm not sure yet what I'll use in the future when I need to actually implement a better method that uses these quadratic constraints. I accept suggestions.
Well, thank you very much again, Ricardo. Spiegelhalter.